end of what I need to get done. So then I can book this and open up with what I need to do for this class. But for this lecture, as I already alluded to last lecture, was I want to open this up to effectively be the formal lecture where we introduce the data lab that you should have already started working on. So if you hadn't started working on it, or if you're kind of confused about some of the tooling or some of the concepts that are given to you in that, I want to kind of cover that very briefly and then give you the opportunity in class to group up and work on the problems that you still have left. Did anyone finish the data lab by chance? Perfect. This will be a perfect lecture then for you to actually make some good progress on it. So the big thing about data lab is it's going to really hone in and challenge you on what we've been lecturing about for the last couple of weeks, which is going to be this concept of bit level representations, in particular bit level representations for integral data, but sometimes just for a sequence of bits, so bit vectors as well, and performing Boolean algebra on it. So, of course, the purpose of this assignment is so that you can familiarize yourself with Boolean algebra in a very practical way, right? It's one way for us to lecture about the concepts, but typically by doing it is where you actually learn the intricacies and the real logic behind something. So when you're forced to be a stakeholder and execute on it. And so I think that's why labs are so good. I think that's why it's good to have labs in Java 1. That's why I think it's good to have labs in Java 2. I think that's why it's good to have labs in 2467 system programming concepts. In fact, I think every class would benefit if it had very strong practical coding components in addition to the theoretical components. And on top of that, we want to ensure that everyone understands the bit level representation of integers. Recall there's two different types of integer representations we have, right? One for unsigned and one for signed integers. One of the fun things about this lab is it's supposed to be a series of riddle-like challenges. So here you get a chance to try to solve some programming puzzles to understand the machine level representations, and it's supposed to be kind of in a fun way if you like puzzles. So if you think puzzles are fun, you'll really enjoy it. If you think puzzles are frustrating, then you'll be very frustrated with this lab. And then also, this is going to ensure that everyone really learns how to use their bitwise operations in C. And again, if you want to consult the textbook for the chapters, it's going to be chapter 2, really. And really the chapters we discussed early on, sections 2.1 and 2.2 inside of our systems book. So just some quick instructions. You're going to want to use your web terminal to access the systems lab for all of the labs. For a lot of the labs, you might not realize that there might be some background services that are running on systems lab that facilitate you to be able to accomplish the lab. So we don't really have it set up so you can run things locally. So I do recommend that everyone use the web terminal. So you can log into the web terminal using your UNO credentials. You should have done this before. And so one of the beautiful things about the web terminal is it's actually a full GUI OS experience. It's an Ubuntu environment. So that means that anything you have to import into your system, you could either use the shell to do that, or you can just open up a browser. And so for some instances, it makes sense to open up the browser, like to submit to Autolab. So if you do need to access web applications, if you need to access web resources from your web terminal, from your systems lab home environment, you can do that the same way you would in a windowed like Mac OS or Windows, right? You can just go from applications to internet and either use the Chromium web browser or the Firefox web browser, and then log into either Autolab or GitHub, because I put all of our course resources, all the data lab stuff should be inside of the repo. So you can download it onto your machine that way. Of course, we've seen Autolab before. Here. This is just showing you how you can navigate through Autolab. And so here, I did not attach these through Autolab like I did last semester. I have them attached in our GitHub repo. So all the course material should be in one spot where you can easily keep pulling it as it gets updated. But the important thing is when you finally get this datalab.handout.tar, the important thing is that's going to be your collection of starter files. So once you get that on your systems lab, you can go ahead and extract those files. When you extract those files, you should have these collection of subfiles here, or, you know, for on the shell, we could view it this way as well. So let's kind of walk through what some of these files are. So again, the objective for these puzzles is you are to only use straight line code for the integer puzzles. What is straight line code? That refers to code that doesn't have any control flow constructs. You're not allowed ifs. You're not allowed if-else statements. You're not allowed switch statements. You're not allowed any repetition statements like for loops or while loops or do while loops. So you're only allowed the primitive set of operators. So you're limited to, in fact, the C arithmetic and logical operators. So like I said, no loops or conditionals. You're allowed to use the bang operator, your bitwise AND, your bitwise XOR, your bitwise OR, your addition operation, your shift left, your shift right, and your negation operation. And so you also, one other rule you should be aware of, because it's going to be one of the one of the more challenging problems is relying on this constraint. You can't have any constants. And when we're talking about constants, we're going to be working with bit vectors. You can't have any bit vector that's longer than 8 bits. So you're only going to be working with bytes. So you're going to see in one of the problems, you're going to have to construct a certain bit sequence that's going to extend multiple bytes. And you're going to have to learn you're going to have to problem solve how to craft that using 8 block bits. So starting with 8 bits, manifest it, and you'll see when we get to that problem, you'll see what that looks like. So there's one problem where that will be kind of an issue for you, part of the problem domain. So let's actually look at what these problems are asking you to do. We can kind of break the set of puzzles, if you want to call it that. I think that's a good word choice for that. We can break it into 3 types of puzzles. The first type of puzzle will be logical puzzles. These are going to be the problems that primarily involve operations that deal with Boolean logic. They're operations that often, or bitwise operations, they're often used to evaluate or produce Boolean values like true, false, 1, 0 in the context of bitwise operations. They can also involve operations that manipulate our bits without changing the numeric interpretation. So you're going to see this is pulled directly off the lab document. You have the name of the function that you're going to implement. So what we're going to see is you're going to have a bits.c source code file that's going to have stubbed out code. So it's going to have a lot of empty source code file, a lot of empty functions that you're going to have to actually implement. And there's kind of some directives, some comments on how to implement those. So there's going to be a description on what the intent for each of these are. So in this instance, we have what? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 challenges for you in the logical set of puzzles. So for instance, on the first one, it's going to be a bitwise OR operation where you have to do effectively this computation, taking an X and a Y, which are our bit vectors. You have to produce the result that would do an OR, but the trick is you don't get the OR. You're limited to only being able to use the bitwise and the bitwise not. Does that make sense? So it's how can you use those operations to mimic what you would get from the bitwise OR operation? And so just to give you a hint, there's a concept you probably learned about in discrete mathematics called Morgan's law that would probably be useful for a problem like this. Okay, so in this instance, you have your point value for each of your problems. And then here, it's not just also, the challenge isn't just like many puzzles. It's not just about getting the correct answer, but doing so using a number of operations that doesn't hit your max. So here you're allowed 8 operations for you to be able to get credit for this. So you have to not only figure out a way to do this conversion, but you have to do the conversion in a way that is under this max operations count. And so here, after that one, we have the bitwise AND. which is going to kind of be the inverse of the other one. You have to do the equivalent of bit X and Y using only the bitwise OR, and the negation, excuse me, and the effectively the bitwise not. We have the XOR, and again, each one of these is going to show you what you are limited to being able to use. Then you're going to have is not equal. So here you're going to return 0 if X is equal to Y, 1 otherwise, right? We're checking for not equality. We're going to have copy the least significant bit. So here we're going to set all the bits of our result to the least significant bit of X. So notice this is only taking in 1 parameter as opposed to 2. We have special bits, which has no parameters. This is going to be the one I was mentioning before, where you're going to have to return a very specific bit pattern of this. Now, notice that pattern you can't hard code because it's larger than 8 bits. So here you'll have to use operations to create this sequence pattern and then return that. Here, you're going to have an opportunity to try to implement your version of the conditional operator. So recall with the conditional operator, X is a truthy value. It's either 0 or 1. It's going to be something that's either truth or false. And if it's true, then you would return Y. And if it's false, you would return Z. And then finally, bit parity. This is going to return 1 if X contains an odd number of zeros. Then the second part of Data Lab is going to be more arithmetic puzzles. These are going to be problems that deal with the arithmetic properties of numbers. They can invoke operations like addition, subtraction, finding the maximum value, negation, checking the sign of numbers. These operations change the numeric interpretation of bits. And so again, pulled directly from the Data Lab PDF, you can see we have the set of functions that are stubbed out initially that you'll go ahead and implement, and then a quick description for what those functions are. We can see the total number of points. Oh, I didn't put the total number of points for the first part. Well, the total number of points, I think, after everything's said and done is effectively, I want to say 40 points is what the lab's worth. And then there's a bonus component, which is the third, if not mistaken. I think these are bonus points. So it's worth 40 points between parts 1 and part 2, and then we'll take a look at part 3, which is optional, and then can append an additional 10 points to your lab grade. So on this instance, you have -1. Notice no parameters. All this says is return a value of -1. We have Tmax, 2's complement max, which is going to return the maximum 2's complement integer that you can create. We are going to have, again, this doesn't have any parameters, so it's something that you can just compute and return the value of. You have negate X, where you were going to turn -X without using a negation operator. You're going to use is negative X and is positive X, and these are kind of related. It's going to return, the first one will return 1 if X is less than 0, otherwise it will return 0, and is positive will return 1 if X is greater than 0, otherwise it returns 0. You have your bang X, which is going to compute the bang operator on N without using the bang operator. You're going to have add OK, which is going to determine if X plus Y can compute without an overflow. And then finally, an absolute value of X, which is going to be, well, the absolute value of X. And again, the max number of operations and the number of points that each of these are going to be worth. And then finally, we have some bitwise puzzles that are primarily deal with manipulating the individual bits or groups of bits within a number. They can involve operations like counting the number of set bits, swapping certain bits, or shifting bits. So here, there's 3 problems. They're worth a total of 10 points. These are the bonus ones. In bit swap, you have an X, an N, and an M. This is going to swap the nth byte and the mth byte with the m byte with the X vector. So X is the vector, your bit vector. And so N and M are going to be the positions in the vector that you want to the bit vector that you want to swap. For bit count, you're going to pass in a bit vector, and so we're going to return the count of the number of ones in that word. And then finally, your logical shift is going to take an X and an N. It's going to shift X to the right by N using a logical shift. Okay, so after you have implemented all this, let's talk about how you can actually evaluate and see if you have the right answers, and talk about submission guidelines. So you should comment all of your solutions detailing why your code works, like what the logic behind it is. So technically, to get full credit for everything, you should pass the test. There's going to be automated testing both through Autolab, but we're going to include the same test that we use in Autolab as part of the package you're going to download as part of this tar file. So make sure you pass all the tests. Use only the legal operators, which we have a script that will go ahead and evaluate your code to make sure that it is meets the expectations, and to also have explanatory comments. Okay, we already know a little bit about the auto grading tools, but let's talk a little bit about the code that we can use to actually check the correctness, to actually check to see if our solutions are right or not. So we have this B. So if we go ahead and from our directory, there's a make file, we can use the shell to invoke the make file, which will then build out the applications that we have defined inside the make file. This will create an executable. One of these is going to be btest. We can run btest, and that it'll evaluate all of the functions inside of bits.c. We can also try to test for a particular function. So if I pass this flag -f and then give it a function name, I can just test that one function to see if it's correct or not without having to test everything. I can also test with certain parameters. So I can do btest, then -f and add a function name, and then do -1 and -2, and then give the appropriate arguments that I'd want to pass for that particular function. And a lot of this you might want to be able to get to this level of testing, because you should get some responsiveness when you test against the testing. So if you're playing around with your code and you want to see if it works, you can test it against particular values. Now, remember, you want to rebuild btest each time after modifying your bits.c. An example of what this would look like initially with your stubbed out code would look like this. So if I just run btest after I do the make, everything should fail, right? Because nothing's been implemented yet. And then at the very end up here, you could see out of the total points of 50, that's including the bonus points, right? So you can get 50 total points, I have 0. Now, if I were to run this again and actually go ahead and build up my solutions and implement them, this is what my output should then look like, where it'll give me all the various points that something's worth, the amount of points that I have accumulated, my total number of points. So in this instance, I've collected all 50 of the 50 possible points, and it'll show me what my point allotment is for each of the individual functions that I've implemented. Now, we also have DLC that's going to be for the coding rules checker. So this will verify the compliance with the coding rules for each puzzle, because it's not just about getting the right solution, but also ensuring that you adhere to up to the max number of operations. So this checker will check to make sure that none of your functions exceed the number of operations they're allowed to utilize. And so the behavior of this is going to be slightly different. It's going to run silently unless it detects an issue, such as an illegal operator or too many operators, or a non-straight line code using some kind of conditional logic. So in this instance, this is a version of a successful run. If I run DLC and then bits.c, I pass it my code, it should just silently prompt me for another instruction. Now, if I violate any of those rules, you'll see I'll get these kind of outputs. In this instance, I get warning, 6 operators exceeded when there was a max of 3 that was allowed. And you can see here, it shows me in particular which of these functions is causing that, special bits in this case. Or bit count, 42 operators exceeded the max of 40. And of course, If you want to run these side by side, both your B-test and your DLC, to compute the correctness and performance points for your solution, you can just run this Perl script driver.pl. And so let's see if I have, and here you get to see when I execute this Perl script, it's going to go ahead and run through the build sequence. And then it's going to show you your final output performance here. And again, that's what Autolab is effectively going to use to allot you your points. And this is a version where we get 0 points subbed out. And then this is the same thing with a fully implemented version of what it would look like, where it shows the number of points, the rating for the amount of points you can get, the number of errors, the performance points, and the number of operations. And then when it comes time to submit this into Autolab, all you have to submit is the bits.c source code file. You don't have to package this into a tar or anything. You should just be able to submit it just by itself. And again, just log into Autolab using your UNO credentials, navigate to CSCI2467, go to the data lab, go to submit, and pass it your bits.c file that you've implemented out. Now, this, I think, project does have a scoreboard, so you can actually compare your performance to that of all of your peers. So you should be able to click on the scoreboard link to see how everyone else is also doing. Excellent. So just some general advice. For testing purposes, you might be printing out values, but when it comes time to actually evaluate the correctness using the scripts, remove any print statements. That means that you won't need to include a standard input out header file for this, right? Because our application is going to use your application as effectively an API. It's going to compile it, and it's going to try to invoke calls to it and see if it gets the expected values back from it. That means if you do put print statements in there, it could mess up the grading scripts and actually mark things wrong when it's actually correct, because then you're littering up the standard output buffer, right, with data that we don't want in there. So keep in mind, it's okay to use print statements when developing, but when evaluating, either remove them or comment them out. And so at all times, it's good just to kind of test and evaluate using these B-test and driver applications. And let's see. Oh, and then that's it. Okay, so at this time, I'm going to ask everyone to now assemble into groups and start working on the data lab. And I will say, when we get to the 10 to 15 minute mark, I will allow you all collectively to try to identify one problem that you want to walk through in class. So I'll give you a chance to kind of look over everything initially. We'll spend the very tail end of class actually showing one solution. I'll leave it to the entire class to decide what that is before we end. Let me see. So I have a question. Are these slides posted anywhere? I'm assuming these slides are posted at the link that I have on the I might have these slides posted. I don't know if I posted these slides or not, because the tail end of these slides have solutions on them. So I think I might have been hesitant on sharing them. But I can post the front half of these without the solutions.
Yeah, I took a look.
And I'll pause the video at this point. Okay, looks like we're out of time for lecture today, but like I said earlier, collectively come to a consensus through Discord on a question you want me to go over at the beginning of next class, and I'll actually go ahead and we'll walk through a particular question with the solution. But the thing is, I'll show you the solution, just not in C. I'll show it to you in Python. And then you can map that logic to C. But it's got to be a consensus. So the class collectively has to decide which question you want me to cover next class.
I'll give you a hint. Pretty much the first half of the